Okay. Well, the answers don't look too bad on here as well, so I'm looking forward to going through a great. Okay, but anyway, let's go ahead and get started with today's lesson, which I have written up for is talking about inverse trig functions. So I'm going to be describing these functions, and I'm also going to be explaining the derivatives of these. They take considerably less time than the trig functions do. At least to explain, because we kind of built off the same foundation. So I'm going to show those all this. Okay, so drawn up here, I have 3 different graphs. Okay, who knows what each of these graphs are? What's this the graph of? Sine, yeah, sine. So this is sine x. What's this one? Cosine, good. And that's because this one starts at 0, this one starts at 1. There's kind of a distinction, even though they look the same. And then what's this graph? This is tangent. Yeah. We didn't get the book doesn't really talk about graphing this, which is understandable considering it's got a whole bunch of asymptotes, right? At these points, so I wrote that tangent's the same thing as sine over cosine, right? At pi over 2, for example, sine is 1, but cosine is 0, so you have 1 over 0. So that's why you have all these asymptotes to go through. But these are the graphs of sine, cosine, and tangent. And of course, we have our other 3 trig functions, but luckily, no matter what book you talk about, they just don't care about the inverse trig of the other guys, because they just don't show up as much. So we have these 3 graphs. Now, when we talk about inverse functions, right? We're talking about basically what if I have a function f, let's say, right? Well, actually, so let's say I have a function f, right? And its inverse function, I'll label f inverse, right? What happens? So the reason that we can say these 2 things are inverse is if they satisfy the following condition, which is if I take f of f inverse of x. So remind me, what's this? What does this mean? It's composition, right? We're composing functions. So I'm saying f of f inverse. So I see what f inverse is and I plug into f. What should happen is this should just spit out x, because the f's kind of cancel each other out. Similarly, if I flip the order around, it'll still be the same thing. Okay. Now it seems like, well, that seems weird. Shouldn't it be the same either way? But depending on the function, it's very important to make sure that both of these are satisfied. Because one example, so let's talk about y equals x squared, right? What is the inverse function of x squared? Good. Well, yeah, so one thought is to say, okay, well, you have a square root of x. I'm not sure if it's plus or minus though. And that's kind of where the issue comes in, right? Because what I want to happen is if I'm taking f of f inverse of x, I should just get x out of it. But if in this case, for example, if I let f of x be x squared and I let f inverse of x be plus or minus the square root of x, if I take f inverse of f of x in this example, I get plus or minus x. That's a problem, right? Because I just plugged in x squared in here, the square root gets rid of the square, but then there's a plus or minus, right? Because essentially, in order to fully have, if I'm considering the entire graph of x squared, the inverse should look like this. But what's the problem with this function? It's not a function, right? It's not, because it fails the vertical line test, right? So whenever it comes to the inverse of some functions, in order to make sure that it satisfies the necessary conditions, what we do is we restrict it. So I say I'm gonna take this bottom edge off of the curve. But as a result, since I restricted this curve, I have to restrict this side as well, because it won't have a corresponding inverse. And so the result of what we've just done is now that they're both functions, even though I had to make a restriction to still be able to work on kind of the domain and ranges that we are functioning in. And so we're going to see something similar here. Now I've drawn these orange lines on each picture, which is the line y equals x. Now some of them are a little weird just based on how I drew the graph, but in each case it's the line y equals x. Whenever I want to get the inverse of a function, or if I want to see what it looks like graphically, all that needs to happen is I need to take the graph I have and rotate it about that y equals x line. So in the case of sine x, my inverse is going to look like this, right? Cosine is going to look like, let's see. So we're going to want something like, maybe we should do it over. Let me check. Let's go. Okay. So it's going to be like this. Okay. And then tangents is going to look like this. Okay. What is the problem with these three red functions I just drew? None of them are functions. Again, they very clearly violate the virtual line test, right? If we run our arm across it, you're going to hit these same points several times. Okay, so whenever we're dealing with when we're dealing with the inverse trig functions, right? We're looking at this function, we want to limit it. So we want to only take a certain section, right? So generally what they do, right, or what we do to be able to get all of our values is we have standard ranges for the y's. And those ranges are as follows. So, you mind if I erase what's here? So, we have three inverse functions to consider here. The first one is arc sine of x. Okay, now this arc, the capital A is actually pretty important. The book emphasizes because if I just put when it's lowercase, that does actually take everything on this curve, right? But as such, it's not a function, so we don't want to work with this one. So y equals arc sine x is the inverse of sine. So that means that if I take arc sine of x, that's going to give me x. And similarly, if I take sine of the arc sine of x, that'll also give me x. Okay. Now, in order for this to work properly, I need to restrict my y. And so the range of this function goes from negative pi over 2 to pi over 2. Now, the reason why we choose those values in particular is because, so if I take, so that would basically be, let's say that this is y equals pi over 2, and this is y equals negative pi over 2. Okay. So, that's a little low. That's going to cover, if I just consider those values, that's going to cover all the ground I need to, right? it's going to give me all of the possible kind of corresponding values in the section that I want, right? If I just keep going up, I'm going to keep getting the same values over and over again. So all I need to consider is section. So in this case, I'm just going to consider, which I'll do. This section of the graph. So this little orange piece here that I just colored in is my capital A arc sine. Okay, and so it properly fits with what we need to, what we needed to. Similarly, we're going to have two other functions. So we have y equals a capital arc sine of x, and we're also going to have cosine of x and our tangent of x. Okay. Now the ranges on these ones, right? The range for cosine, what happens is that we want to be able to get the same values, right? But I can't do the same section because that would only give me, in this case, from here to here. And so that's only giving me half of the picture. So what I want to happen is I'm going to take from 0 all the way to here. So the range for arc cosine is 0 to, and then finally for arc tangent, we have all these separate little pieces that go all the way from the left to the right, but I only need to pick one of these. So the easiest one is just to pick the one that's right at the origin. And then remembering this line is going to be is also 2, and this line is y is minus pi/2. So our tangent has the same range. Okay, so we're going to have a few example problems here, but the big idea at this point is whenever I'm finding arc sine, arc cosine, and arc tangent, I only have a select number of y to choose from, right? You may say, for example, right, so I'll do a first one real quick with arc sine. So let's say we're looking at arc sine of -1. Okay. So if I'm looking at arc sine of -1, this is the same question, right? If it's kind of hard to interpret what's happening here, this is the same thing as saying the sine of what angle gives me -1, right? This and this ask the same thing. Okay, so our goal is to figure out what angle I can put into sine that's going to give me -1, right? Because what the arc sine does is it takes whatever we get out of the trig functions and kind of takes it back, see where it came from. Okay, now based on the table we've been using quite a bit, kind of going between 0 and 2 pi, initially you might say, okay, well, theta would be 3 pi/2. However, since we've restricted the domain of arc sine, or restricted the range, sorry, we can't use 3 pi/2, right? Because we can only go from -pi/2 to pi/2, and 3 pi/2 is greater than that. So we have to consider what its equivalent angle is in this range, which would be -pi/2, right? And that's because if I have my graph, right? And so 3 pi/2, right, is the same thing as 270 degrees. And so that would be down here on this line, right? So this is 3 pi/2. But this is also the same thing as going an angle of -pi/2 down to that line. So instead of using 3 pi/2, I choose to use a -pi/2. Okay. And that's purely because we used this capital A in describing it. Now, technically, if it was just a lowercase, then 3 pi/2 would be fine. But with these specific functions, we define a specific range. So please keep that in mind. Okay, so let's see what other examples we can run through here. Okay. Let's see, trying to make sure. Okay, let's see what's all about this erase. For now. Any questions so far on all this? Hopefully it's not too bad. Yes.
Can you just change?
Can you change the range?
Yeah.
Not really. It's kind of, we have these sort of universal ranges for them, and so, I mean, you could change the range, but then you'd be kind of against the standard, and so then it would make things confusing. Yeah.
I might be remembering this wrong from trig, but for arctan, isn't it supposed to be parentheses, not brackets, like it doesn't include? Or
That's
no?
correct. Yes. So that's my bad. Thank
Okay.
you. Why is that? Yeah, no, go ahead. Okay, that's fine. I was just curious. Anybody have any idea why that is?
The asymptotes on the graph?
Good. So why, so pi over 2 and negative pi over 2 are the asymptotes, right? You can't get those angles, right? Because if we try to say, if we plug pi over 2 in the tangent, that doesn't work. Because you're going to get, this is the same thing as sine pi over 2. Cosine pi over 2, which is 1 and 2. Which in this case, I mean, you could do a limit and say that it approaches this, but as tangent of pi over 2, it doesn't exist, right? So in the case of arctangent, we don't include the negative pi over 2, negative pi over 2%. Thank you for clearing that up. Any other questions so far? Does that make sense? Good. Okay. So let's go through a few sort of angle examples here. So the book gives 3. We have arc sine over root 2. We have our cosine negative root 3 over 2, and we have our tangent of negative root 3. Okay, so you'll have problems that say find these values. Okay, and you're just gonna have one answer because it has just a specific range, so it only goes to one value. It does not go to, right? You won't have multiple angles that give us 1 over root 2 since we have a certain range. Okay, so let's look at first arc sine of 1 over root 2. Okay. So this is asking the same thing as the sine of what angle gives me 1 over root 2. Right? So sometimes it's easier to think about it this way. We're finding the angle that's going to give us 1 over root 2. Now, if this looks a bit unfamiliar, don't worry. If we rationalize it, we get root 2 over 2. 40, good, 45. So theta, so arc sine of root 2 over 2 is, now we'd say, I'll put in kind of parentheses here, but 45 degrees. We need to put that in radians though, because radians is the proper range to use. So how do I convert that to radians? Good. I multiply by pi over 180. What do I get when I do that? Pi over 4. Good. So arc sine of root 2 over 2 is pi over 4. Okay? Is that good? Right? So always, if you need to, just rewrite the statement so you know kind of what you're looking for. And then hopefully the table should come to mind, or some values you do recognize in some way. If they give you a value that's not on a table from here, it's most likely because you just got to put them to a calculator, because we can't memorize all of those. Okay. So this one's off the list. Let's take a look at our cosine of negative square root of 3 over 2. Okay, so now we're looking at this one, right? This is the same question as cosine of what angle gives me negative root 3 over 2. Okay, now we'll come back to the negative real fast. Let's talk first about the cosine of what angle is going to give me root 3 over 2. Good, 5 or 6. So, okay, well, actually, I'll write. So, theta is pi over 6 would give me this angle, right? However, we don't want the positive of it, we want the negative sign. So if theta is pi over 6, then we get cosine theta would be. So how to fix this is the question. So how to figure out what the angle is that actually give you the negative counterpart. So what is it? Good. So that's correct. So let's talk about that real quick, right? So as a reminder, right, our cosine has a range from 0 to pi, all included, right? So in terms of a graph setting, that's everything within this upper section, right? Within this upper circle, essentially. So if you hopefully you remember from trig that each of the quadrants on this plane has a specific kind of letter attached to it. Maybe you've seen ASTC before, which means all students take classes, all students take calculus. It depends on how people learned it. But the A here means all. So in this section, every trig function is positive, right? So if you take an angle and plug it into the trig function, it's going to give you a positive number. Similarly, so, and then from here, sorry, S is sine, so only sine's positive here. T is tangent, so only tangent is positive here. And then C, cosine, only cosine is positive here, right? So if we want to get a negative cosine within the range that we're given, it has to be within this quadrant. Okay, so what happens in our case is that pi over 6 becomes our what's called a reference angle, right? And that reference angle, right, we look at the base value and say, okay, there's an angle in this first quadrant that'll give me this value. So you find what that one is, right? And then you figure out, okay, let me see what quadrant I'm in or what quadrant I need to be in. So in that case, we need to be here, right? Because it only has this range. And so if it has a choice between this one and this one, we want it to be negative, so it's here. What we do with that reference angle now is I come up on that side from the horizontal. Okay? And I'll kind of make this right color. And I come up that reference angle, which is pi over 6. So in order to get the negative equivalent of that value, I just do to get this value here, all I need to do is take pi, which is the whole angle, and subtract pi over 6 from it, which is what I said. So I'm going to get pi minus pi over 6. Okay, how do I subtract this? What do I need to do? Common denominator, good. What's the common denominator going to be? 6. So we get 6 pi over 6 minus pi over 6. So what's that going to be? 5 pi over 6. Good. And so this is going to be a general rule, okay? I want to show why, but this is actually going to be the case. If you're working with arc cosine and you want to get the negative value, you just take kind of your reference angle, the one that would be in the first quadrant, and subtract it from pi. So if you know pi over 6 gives us root 3 over 2, just subtract it from pi, so get negative root 3 over 2. The nice thing also about sine and tangent is if you want their negative values, all you need to do especially since the range is nicer, just put a negative sign on the angle. So it's even easier. Okay, which we'll get to that when we talk about arc tangent. Okay, so arc cosine, good. That's 5 pi over 6. Okay. Finally, arc tangent. Okay, so I need to get square root of 3. So this is the same thing as saying the tangent of what angle, right? Gives me negative root 3. Anybody, any guesses on what, remember what the angle is that gives us root 3 for tangent? Possibly. What is it? Right. So it's gonna be pi over 3. So if that's not clear, remember tangent's the same thing as sine theta for cosine theta, right? So what we want to happen, right, is I want the top part to have a root 3 in it, and the bottom part to just have a 1 in it, right? Because I'll get root 3 over 1. Which, if you remember your table, you could also get all the tangent values on the table, but just having sine and cosine, you'll see that the angle has to be pi over 3 or 60 degrees. Okay, because you would get here, you would get root 3 over 2 and 1 over 2, which when you divide those gives us root 3, right? But again, I want negative root 3, so what do we have to do this? Not in this case, that's for cosine. Cosine's the only one that does that. For sine and tangent, just throw a negative sign on, and you're done. So pretty simple. Okay. Probably some of this is a bit of review, but is this making sense for people? How this all works? Okay. So just say sine, cosine, tangent of some angle gives me what I want, right? Figure out the angle that's going to give you kind of the positive value, and then make the corresponding change by either subtracting from pi or just putting a negative sign on it if you want it to be the negative value. Good. Question? Awesome. Let's see. Don't want to. I think I'm gonna do kind of the equation example, which I might do if we have time at the end. But what I want to focus on right now is what happens when what happens when, so clearly if I have arc sine of sine of x, that's going to be 1. What is it? It's x. Yeah. And similarly, if I do it the opposite way, what? Yeah. Okay, but we want to be cautious about this a little bit. I should mention, I guess, before I get to the other part, right? Because technically I could have sine of, so I'll do a quick example here to demonstrate what I'm talking about. What if I was doing this? Is that going to be 3 pi over 2? No, it's not, right? Because our sine 3 pi over 2 isn't in the range, right? What is the sine of 3 pi over 2? What is it? So the answer is going to be negative pi over 2. But what's the sine of 3 pi over 2? Just this part. Negative 1. And we already talked about this one. This has to be negative pi over 2. Okay, so another way to look at this is it's still going to be the same in the same place, but you might need to subtract 2 pi from it, or just fix where it's at so you can get the correct angle. Okay, so a little bit of caution with this one, but luckily this guy always works. Okay, but our main concern should actually be if I have something like this. Okay, they're not the same now. There's not, you don't have sine and arcsine, you have tangent and arcsine. Okay, so the issue becomes, what do I do in a situation like this? How do we handle this? Okay, so let's remind ourselves real quick, right? So we've defined these arcsine, arccosine, arctangent functions, right? But what do these give us, right? When we've been solving for them, it's always been giving us, they give us angles, right? These are angles, right? So arcsine, arccosine, arctangent are angles, right? So if I imagine I have a triangle, right? I have an angle, which is this arcsine of 2x. Okay. Now, that triangle, right? Remember, whenever we're solving this equation in particular, this is the same thing as saying that the sine of theta is 2x. Right? So arcsine of 2x is the same as sine of what angle of this angle in particular is 2x. Right? What is sine in terms of a triangle? Not right. Good. Opposite of our hypotenuse. We don't necessarily have a hypotenuse part, but I can split this over one. So now I have this neat ratio that represents the sine of my triangle, right? So the opposite side is 2x, and the hypotenuse is 1. Okay, are we seeing that? Does that make sense? Right? Yes, so we have sine theta as 2x, right? And we're wanting to kind of mold this into an opposite of hypotenuse form. So since I don't necessarily have a denominator on it, I just create one. And so I can call out my hypotenuse. Now you could technically do like 4x over 2 or 6x over 3 or something, but why not just make it as simple as possible? Okay, so remember arcsine again is my theta, and so the sine of that angle is 2x over 1. This is a right triangle. Can I get that last side? Good. Now, Pythagorean theorem. Good. So Pythagorean theorem says that if I take two sides, A and B, square them both and add them, I get C squared, right? So we'll let A in this case be this bottom side we don't know. B is going to be 2x. And C is going to be that 1. We get 1 squared. Okay. Can I solve for A?
Yeah.
We can, right? I mean, I don't have to necessarily solve for A and X, right? X is just some variable I'm plugging in. Basically, what I'm trying to do is I'm wanting to take this expression and write it in a more general, an easier form to look at, essentially to plug into, right? Because having to put an angle each time and go through these two functions is a bit of a pain. Okay, so I can solve for A in particular, right? If I take this, so I'm going to have A squared equals 1, 2x squared, 2x all squared is 4x squared, right? So I have A squared is 1 minus 4x squared. So what's A? Not quite. Remember. Not true. Even if it's minus. Isn't it? Right? So I can't square root both. I just have to leave it. So A is going to be 1 minus 4x squared. Okay. So I have a triangle that has all three of its sides now. It has its opposite side, a hypotenuse, and it has its adjacent side, which always works with Pythagorean theorem, right? No matter, as long as the x kind of fits within, as long as the x makes sense, right? Clearly, it's going to have to be a smaller value of x, because if I put something too big, 1 squared minus that thing squared is going to kind of break apart, okay? But now what do we ask to find in the end? We want to find tangent, right? So I was given an angle, which is arc sine of 2x. From that angle and from the knowledge of what that function does, I got all three sides of the triangle, right? How do I find the tangent of that triangle? It's opposite over adjacent, right? What's my opposite side? 2x. What's my adjacent side? So tangent of the arc sine of 2x is the same thing as 2x over the square root of 1 minus 4x squared.
The hypotenuse is 1.
So I said that the hypotenuse, can't speak. I said that the hypotenuse was 1 because I'm given that sine theta is 2x, right? I just need to find a ratio that works, and the easiest thing to do is just to call this 1 for the hypotenuse. I could have said, let this be 2, and then this would have to be 4, right? So you have 4x over 2, but it needs to be 2x. So then you could have used 4x for your opposite side and 2 for the hypotenuse, right? Because no matter what, even if I use these values, I would get the same thing because the ratio still holds, okay? So you can pick whatever you want for your hypotenuse, just as long as it still keeps the same kind of ratio on this right side. So the reason I chose 1, or I knew it was, or I said it was 1, is that's just the easiest option. Why not just take 2x and throw it over 1? Okay. Yes? No? Maybe so. Let me do another quick example of that. Well, instead with a number this time. Okay, so we'll do sine the arc cosine of negative 3/4. Okay, so we need to do this one the same way. So the first thing I'll start off by doing is saying, okay, let me take this inside piece. And that's going to be my angle in this case, or cosine of negative 3/4. Okay. This is the same thing, same question as cosine of theta. What angle makes cosine of theta be equal to negative 3/4? Okay, is that making sense so far? I also could just get this by doing cosine of both sides, because they should cancel out. Okay, so this gives me a bit of information that I have a triangle with this angle, and the cosine of that angle is negative 3/4. Right now, remind me what's cosine in terms of triangle? Adjacent over hypotenuse. Good. Now, since there's a negative value, technically, I should probably redraw this. So maybe I'll do that for the sake of what we're understanding, but I won't take it off any points if you draw it the other way, because all we need to know in general is just where our values are going. Okay, so I'm going to say, right, this is all radio fraction, so I'll just use the numbers that are there, right? So my adjacent side of my triangle, I'll let it be negative 3, and my hypotenuse, I'll let it be 4. Okay, because the cosine of that angle should be the adjacent side of the hypotenuse, or negative 3/4. You could You could do 3/3 and then -4, but when it comes to hypotenuse, it's nice to try to leave it positive. If you can, I don't want to get the messy business there, so try to make the sides negative if it comes down to that. Okay. Can I find the last side? Good. How? Well, it would be plus -3 squared, right? Because you have to put b inside the square equals 4 squared. Okay, so a squared is 16. What's -3 squared? 9, just positive 9, right? So we get -9. 7. Okay. So we can take the square root and we get the last side to be √7. Okay. So then what's the tangent of that triangle? Or the sine of that triangle? Good. Now, this is the kind of the important reason why I said to don't put the negative here. Because you would have gotten this answer is negative, but it's going to be positive. So keep your negatives on the sides. Okay. Any other questions here? So that's basically the end of 6.4. And then I'll take a bit of time real quick to cover 6.5, which will just be me deriving the derivatives for these 3 functions. So it's not that hard, I promise. It's actually easier than one day. Any questions? And it's more fun than Monday as well. Okay. So when I say I'm deriving these, you're in luck because I don't have to use a forced step process this time. So not today at least. I think Monday I'll have to use it again, but we gotta get more tools in our toolkit to take derivatives. So we need to know all these functions and how to take the derivative of them. So first, let's start by examining our sine. And I want to take the derivative of this. Right now, clearly I don't know what the derivative is right off the bat, right? But I do know what the derivative of its counterpart is, right? What's its inverse function? Sine. Good. So what I'm going to do is I'm going to rewrite this, right? Y equals arc sine of x, right? So I'm saying arc sine of x gives me some angle. This is the same thing as saying sine of that angle y is my x. Right? This is the same question. Okay. Can I take the derivative of this? Yes, we can. How? What is this called when we have implicit, right? So this is an implicit derivative, right? So I'm going to take both sides. Okay. So start with the left side. The right side is really easy, so we'll get back to that. Start with the left side first, right? So what is the derivative of sine of y? So it's going to be cosine of y times dy over dx, right? So you can think about it as, because we have our u sine derivative of sine u is cosine u du over dx, but also we talked about that when we're doing implicit things, right? You can treat the y as x until the very end, and then just slap a dy over dx. Whichever way is easier. This needs to be here because this is an x. Okay. What's the derivative of x? 1. Right. So what is dy over dx? Now this is a problem. And it's not because this is wrong. It's because this isn't really in a form that I like. I want to be able, if I'm taking the derivative of this, just in general, I'm not worrying about implicit, I'd like to be able to just put it in terms of x, right? This is in terms of y right now. So I need to do something to kind of make this work. Okay? So I don't know what cosine y is in terms of x, but I do know what sine y is. It's just x. So I need some ideas here. How could I get sine y? Any identities we have to kind of throw at the wall? What do you think? I need something that relates sine and cosine together. What is it? Not quite. No. What is it? Well, we don't want to take the derivative again, right? We're done with that. There's a certain identity I actually had it as the first one written on the board underneath the identities list. That's very valuable to us. Good. So I'll do y's in this case. This relates sine and cosine together, that if I square both and add them, it just gives me 1. So what I can do is I can take this formula and rewrite it to my own needs to fit whatever I want, right? So I want you to solve for, I want to get cosine in terms of sine, right? So what should I do? Sine squared y, so if we subtract sine squared from both sides and we get this, okay? And then to solve for cosine y, we just take the square root. So cosine y equals the square root of 1 minus sine squared y. So the derivative is the same thing as 1 over the square root of 1 minus sine squared y. What is sine y? It's x. Good. So the derivative in terms of x is 1 over the square root of 1 minus sine y squared, which is the same thing as x squared. So this is the derivative of the arcsine. Okay. It's a little funky because whenever we were doing the trig function, right, their derivative still was a trig function. But now we're doing the inverse trig function. Its derivative isn't quite a trig function. And luckily for us, this works on all the values that we want to for our curve. So this fits exactly what we need. So the derivative of arcsine is 1 over the square root of 1 minus x squared. And I'll write, as we like to kind of put a chain rule form as well. If it's not x, all that happens is I will still have 1 minus u squared on the bottom, but then I just multiply by u over dx instead. So you can think about it on the side, which maybe I'll do that for. We get this. Okay. So I just take u and put it in place of x, but then multiply by du over dx. Okay, just as you would expect it to. Okay. Okay. Our cosine u is going to be really hard to remember because it's very different. Actually, sorry, I'll put that first. It's negative. It's the same thing except there's negative sign over. So it just rotates. Okay, and then of course if we have u, we will get negative 1 over the square root, 1 minus u squared times du. Good. Okay, one more. So if you want to practice getting that with the cosine for yourself, then go for it. Exercise, it's basically the same thing as this, except when you take the derivative of cosine over here, it would give you a negative sign. So the negative cosine. Okay. But now let's look at arctan. This one works the same way. I'm going to have candidate y x. And then I want to take the derivative of this. What's the derivative of tangent y? Good. This is equal to the derivative of x. What? Derivative of x. So on. No, you're good. You're good. So then we solve for dy over dx. I get 1 over the square root of 1. Sure. Okay. So again, we're at an impasse because it's still in terms of y. I need to get it in terms of x. I know tangent y is equal to x. So how can I rewrite how are secant and tangent related? Well, we need an identity for that. Tangent squared y plus 1 is secant squared y. And this one's actually really easy. We don't have to take any square roots. We don't even have to move anything around, right? Because we have secant squared y. So just replace that with 1 over tangent squared y. And then tangent y is x. So we get what? What do we get? Good. 1 over x squared plus y. Or maybe I think the book might say 1 over 1 plus x squared. Doesn't matter. It's the same thing. You just remember which way is easier. Sometimes they like put the constant in front or you just put the x squared in front, but that's okay. So that is the derivative. Hold on. So I'll write the last one on there, but let's just do like a couple of quick examples, right? So if I want the derivative of sine of 2x. Actually, I'll do x. How would I do this? So I'm going to use this formula, which says that it's going to be 1 over square root of 1 minus u. What's u in this case? X squared times du over dx, which is 1. 2. Good. So then my final answer I could write is 2x over square root of 1 minus. Okay, good. Oh, you guys write that down inside. Or can derivative up here. Okay. So now let's do let's do one more. If you're doing the derivative of arc cosine, just imagine it's arc sine and then just throw a negative sign on it. Really no change. There will be some book problems, so you want to make sure the negative sign's there. It's the same. It's gonna be the same. So now if I have arctan, let's make it a little more interesting. We'll do x plus 2. Oh, actually, let's do x times 0. Okay, x plus 2. Okay. How do I take the derivative of this? We need to use product rule because we have 2 different functions of x to be multiplying. So I'll let this be u, dv. What's du over dx? Just 1, right? Because u is x in this case, so the derivative of u with respect to x is 1. What's dv over dx? derivative of x plus 2 is just 1. So that comes just from the formula on the right. So we have u v du over dx and dv over dx, right? When we're doing product rule, the derivative of u times v is u dv over dx plus v du over dx. So what's u? X. What's dv over dx? Good. And then times 1, which is just that thing. Plus, what's v? Arctan, yeah, 2 plus x, or x plus 2. And then what's du over dx? 1. So then this. I encourage you maybe look at a quick look at some of the book examples. There's a big one in there that's kind of like arc sine over x, which really is just remember use quotient rule. And I think they simplify a little bit, but I'm not going to be too big on that. Otherwise, no. Next Wednesday we still have the Wednesday after that we still have 3 sections to go through for it. We're going to be talking about logarithms, exponentials, Yes, yeah. So the way I got this, the derivative of arctan and the derivative of arcsine is because of the formula. Okay, which I derived. I had. They're not here. Yeah. So if I give you a problem and I say take the derivative of this function, and that function has one of these in there, then you have to use that formula. Okay. Thank you for watching, everybody online. I appreciate it.